Thank you to all participants of the seminar. I'm happy to be the first in this part of this series seminars. And it is a joint work. I'm going to present with my students, Jie Ma and Chi Zhao. They are both here. And I will talk today about the special class of networks. It is multiplex networks, and I will start with some brief introduction of what multiplex networks are. And this will be the presentation. The presentation is divided into two parts. The first part, it is without dynamics. So it will be the model of game theory from about multiplex networks and the concept of stability applied to this class of networks. So I will introduce notations, networks, and so on, and discuss some results that we obtained with GMR on this part. Then I will switch to the dynamic part, and it will be the opinion dynamics in the networks with two layers. When we have an external and internal layer, and the internal layer, it is like a hidden layer for all the participants. Now, I will go with a brief introduction about multiplex networks. So here, we all know that people communicate in different, in different layers, even if we communicate in the society, in the social network. So it means that we can be friends, we can be co-workers, and we can go to the cinema, theater with someone. And there are different ways how we communicate in the society. So if you look at this picture, you can see two three-layer networks. And the picture A can be called multiplex network. And the feature of this network is that in each layer, we have the same set of nodes. So one node is represented in all the layers. Yes, so we have here three layers and the same set of four nodes. In picture B, we see three layers, but the nodes can be different in this layer. And this type of network is called multi-layer. So, but of course, the definition of the multiplex and multi-layer network can vary from book to book and in different pieces of literature. So here you can see on multiplex network that the nodes in different layers can be linked by different graphs, and each node in the layer is connected. So you see this dashed line, it means that the same node is connected with the same node in other layers. So it means that we can gain from communication with other players in different types of communication. So this is the idea. So we adopt the definition of multiplex networks given by Corser in this publication. And there are some examples of multiplex networks. So the first and very good example is social network, where we communicate, as I said, as friends, and it may be members of some cultural society, partnership, co-authors, and so on. So this is a good example. And another example is from biology. So other examples can include also gene co-expression networks, protein interaction networks, and also transportation networks as well. Another type of networks, special class of transportation networks, I would say that it is not multiplex, but maybe more multi-layer networks, when you can see here, for example, tube. So if you see metro, you have different lines, and they have some nodes which are represented in different layers, the same nodes. So this will be, again, the good example of multi-layer network. This example we found from the book about nuclear network. So you see here in this publication of Goldblum, it is also a good example I wanted to show you about multiplex networks. They represent the real data of communication between different states. So firms who produce some nuclear technologies. And they said that each state represented in different layers of communication. They called it the first layer, the up layer. It is nuclear cooperative agreements. So we see some simple network here. The second layer, alliances. There is a network of conflicts and trades. So this is the simplification of the real data, and the real data they represent on the data set, open source data set from 1980. So we see here the same set of nodes represented in all these layers. The good news is that in conflict, we have not so many links, so in this graph, but a lot of links in alliances and trade. So we see these multiplex networks. This paper analyzes this network using, the focus of this paper was on the centrality measures of this graph. But we focus on different problems. Also, I wanted to show this one slide about hypergraph, because hypergraph is also now investigated in many areas as well in game theory. So in a hypergraph, it is the definition from Wikipedia. So it is a generalization of a graph when the link may connect more than two players. So for example, here we have 7 nodes, and we have here 4 links. So there are links, for example, if you consider the first link connects nodes V1, V2, V3. So it is this yellow link, so, and all other links. So it is a bit different structure, but it is again a graph structure that can represent also communication, for example, in social networks as well. Now I will give some brief notations and definitions which are needed for the model. We will focus on the stability of networks, and for us, we need to define the network as well. So we have the set of players, capital N, more or equal than 2 players. A common set of players is connected through multiple types of relation. Each relation is represented by a layer in the graph. Each layer is defined by a graph, and we have capital L is a finite set of layers. This set of layer graphs is capital G. So we have these graphs, they are given. Each layer is represented by undirected graph in our model, and each graph from this set L is defined by the same set of players and different set, maybe different set of edges. Also, we define the pair IK. So this is the pair represented player I in layer K. So this pair represents player in different ways of communication. And now we are ready to define the multiplex network. It is given by this set of objects. It is the set of players, the set of layers, the set of P players in the layer, and the set of layer graphs. Now, for example, here you can see this is the 3-layer multiplex network with 4 players. So we see that the players can be connected with different graphs here. About undirected graph, I think you all know this, but I briefly mentioned the notation. G is undirected graph, which is given by the set of nodes and the set of edges A. Ij we will write as a link between player I and player J. If we want to define the path between 2 players, we will write the nodes which are connected. So we have these links from graph G, and we denote by Dij of G the length of the shortest path between player I and player G in undirected graph G. So it is the number of the links in this path. If there is no path between 2 players in graph G, we set this length by infinity. If we write I and this two-side arrow G, it means that players I and J are connected in graph G. So there exists a path between player I and player G. If we write G plus ij, it means that we add, we form a new link where we add, we form a new network where we add a link ij to network G. If we write G minus ij, it means that we delete link ij from this graph. Now I will only specify some network structures that we use in our results. So for one layer network, we consider, we say that graph is complete if for any two players there is a link ij. We call network G as a star if there exists a player, which player I, such that for two different players, J and M, if this link exists in the network, it means that or player J or player M is player I. So player I is the center of the star. And for multiplex networks, we use this definition for the special structures. So a multiplex network we call all layer complete if each layer is represented by a complete graph. All layer star multiplex network if each layer is represented by a star. Here I need to mention that in our results we have two types of multiplex networks. We have all-star network with the same center in all layers, and we also consider all layer star network but with different centers in the layers. A multiplex network is called all layer empty if it is represented by empty graph in all layers. Now I will briefly explain the problem we are examining. So in the networks in game theory, when we consider the society which is connected, it is an interesting question to examine why the network structure is formed and it doesn't change over time. So one approach is to consider the stability condition. So maybe this network is stable in some sense, that this network is not changed by the players. So that is why the stability concept is a key concept in game theory examining networks. Also, there are another concept like efficiency when the network is formed to maximize the total utility or social welfare of the society. But in our research, we started with this research with focusing on stability conditions in these multi-layer networks. First, we need to define the utility function because it is a key definition in the network games, because if we define utility in some specific way, which can explain why the network is stable, it is a very good application of the theory. So I will explain this, and here in our work, we have a very general definition of the utility function. So we assume that utility of any player in a network is represented by the benefits and costs. And utility is a general utility, it is benefits minus costs. So for benefits, this part, players can obtain benefits not only from the players with whom they are directly connected, so they have linked, but also from the players with adjacent nodes are linked, the players with whom they have a path in the network. Since it is a multiplex network, the players benefit from every layer. And the benefit of any player from player I from player J in layer K equals to this amount. So delta, it is a parameter between 0 and 1. It is a common decay factor. And the degree is the length of the path between player I and player J in layer K minus 1. So here you can see that player 1 obtains unit 1 from a direct connection with another player in any layer. And if we assume that the decay does not equal to 1, so it belongs to this interval, the benefits from other players with whom this player is connected decrease with the number of links connecting them. So we see it here. And if there is no decay in benefits, so if delta is equal to 1, the benefit of player I from player J in layer K, if they are connected, is equal to 1, regardless of whether they are directly connected or indirectly connected. So this is a special case. And we examine two cases and consider comparison of the results. Now, more interesting part, it is cost. So directly connecting players pay for the link. So this is the cost for any player. If player has no links, he has no costs and no benefits. So we assume that the cost function is denoted by f of qij. It is the cost function for player I to maintain a direct link with player J, if this link exists in this layer. And qij denotes the number of layers in which this link exists. And we wanted to implement in this theory this idea. The more the layers in which link ij exists, the less the cost of a link between player I and J in any layer. So it means that if we are familiar with a player, so if we have a lot of links in different layers, we can reduce the cost of communication. So it will increase our utility function, total utility, if we have many connections, I mean, in many layers with this player. That is why this cost function we model satisfy the following conditions. So the first condition, it is a decreasing function of Q. So the more connections we have, the less the value of this function. It is a convex function. And the last assumption, it is important that if we have only one link through all the layers, we have fixed costs. It is C and it is given. And if the players are connected in all layers, so L is the maximum number of layers where they can be connected, it should be positive. So we need to avoid negative costs. So that is why we assume this. And we provide three types of cost function. So in our results, in some results, we assume the general way of the cost function only satisfying this condition, as well as we present three types of cost functions satisfying this condition. The first one, it is a very simple one. So we assume that this cost C divided by the number of connections we have with, between players, so the link ij in the whole network. So this is a representation of this cost function, for example, if C is equal to 9. And we have a more, let's say, difficult form of this, complicated form of this function 2 and 3, represented on figures 3 and 4. This is the two-parametric function. The first function, we have this decay, and we have these two parameters. Of course, this is constant C and parameters alpha 1 and alpha 2. And here we represent the graph of this function for different values of these parameters with the same C as here, it was 9, and here you see the same value we started from. So for Qij equal to 1, we have this fixed cost, for example, 9. And here we wanted to have exponential decay. That is why we get this exponential function and show how, depending on the parameters, we have the function satisfying these properties. Of course, this the form of this function is not friendly to examine some conditions, and we show that we are limited in getting some results, explicit results, if we have these cost functions. And when we calculate utilities, you see that the utilities in layer K can be calculated as the, you see here, the benefits minus costs. And three different costs will give us three utility functions. And if we summarize the utilities of any player in the whole multiplex network, we can get, if we assume that this function is additive, we can get these three types of utilities for the players in multiplex network. Now I will represent you the notion of the stability concept and as well-known concept of stability was represented. It was represented by Jackson and Walensky. It was defined for the one-layer network, and the network is called pairwise stable if these two conditions they are satisfied. So the first condition means that if link exists, nobody wants to delete this link because they cannot gain from deletion of this link. And the second condition, if the link does not exist, nobody wants to, this link cannot be added because, let's say, nobody, no pair of players can gain from creating this link. And I would like to specify that for creation of link, both players should be involved, for deletion of the links, only one player can delete a link. And this idea of pairwise stability is close to the Nash equilibrium, but applied for the networks. We give two definitions of stability. And the first definition is defining the stable network, multiplex network, if you consider the vector of utilities. So if you assume that, for example, you consider all your utilities like, utility in each layer is represented by a number, you form this vector, and we call the multiplex network G all layers stable if you cannot gain by deletion of links or adding links in any layer. So here it is a formal definition of this stability. The second approach, if we summarize the utilities in all layers, as I presented here, we have one utility function for the whole network. And this stability is very close to, it is the same like pairwise stability. We call network G stable if addition of link or deletion of the link is not profitable for the players. When we consider one utility, it is a number for any player. So we have two notions of stability for multiplex networks. And the first problem we examine is the relation between these two concepts of stability. Stability, like definition 4 and definition 3, gave us all layer stability. And proposition 1 gives us the condition when from all layer stability we can get the stability conditions. So we need to satisfy this condition 4. And these conditions say that if there are, we need to check this, if there are unconnected players in one layer of an all layer stable multiplex networks, then we need to verify this, that if the decrease in costs by making a link not larger than the decrease in a player's profit in a layer where players create a link. So we only focus on one layer here. And if we consider the second item, so for opposite conditions, so if multiplex network G is all layer empty, only in this case we can prove the stability of G. The stability of G implies the all layer stability. So this is a very strong condition that we need to satisfy, that we need to have all layer empty network to guarantee these conditions. This is written here, and I will present the results about stability. We focus mainly on the stability when we have one utility. Here I will first present the results about benefits without decay, so delta is equal to 1. We have this utility function, the first utility function here, and we present these results. So we focus on special network structures because you can imagine that to check all possible structures. It is impossible, so we focus on some structures and I represent them. So if multiplex networks is all layer complete network, it is always stable. The same we can say about all layer star network with the same center. But for example, if we consider a two-layer multiplex network with a star with different centers, to have it stable, we need to satisfy this condition. So the cost for forming a link in one layer should be less or equal than 1. And if we extend this result for the L layer network with the same star in L-1 layers and different star center in one layer here, so we need to satisfy this condition for stability. So if C is less or equal to n-1 and the number of layers, it will be stable. And now if we focus on the second pair of function, utility function with benefits without decay, we can get, we cannot check all the conditions, like here for different networks. We focus on two structures. And the first one, it is multiplex networks, which is all layer complete. And it is never stable with definition 4. So for this utility, we cannot get this stability condition. If this condition is satisfied, then a multiplex network represented by the star with the same center in all layers is stable. And I will show you, because this condition is not so nice, I will represent you on a graph this condition. So you see here that for different parameters, value alpha 1 and alpha 2, we get this area, colored area of stability. So we can see that it is not bad, because C here on X, Y, we have C, and C has a limit. And we represent here the limits of C for different values here. Now I will represent results with exponential decreasing function here. It is utility function 3. And we again get results for all layer complete network. And now it can be stable in comparison with the previous proposition. So this formula, yes. So when we have exponential decreasing function, we will get, sometimes we can obtain this network as stable if this condition is satisfied. As you see, it is interesting that this condition involves only alpha 1 parameter, and alpha 2 is not involved here. For the second part, we get the stability condition. When this inequality is satisfied, we get the stability of a multiplex network with the same center in all layers. And again, we show this stability condition, again, colored area. You see, for example, for alpha 1, which is equal to 0.8, almost all the plane with positive values C and L satisfy this condition. So we see here. And we summarize in table for all layer complete and all layer star network with 3 utility functions, the results to compare this function. So for utility 1, we have always these 2 network structures are stable. With utility 2, all complete never stable, but it may be stable with utility 3. And for all layer star network, we have these conditions to be satisfied. But as I need to mention, these conditions cannot be compared. So initially we wanted to compare them, but alpha 1 and alpha 2 has different meanings here. So there are different parameters. That is why we do not compare them. Now we switch to the case when benefits have no decay. So delta belong to the interval from 0 to 1. We exclude value 1. And we get the following results. So if we have this simple formula 1 to calculate utilities, for the case with decay, we have these 4 results. So multiplex network represented by complete graph in all layers is always stable. the second condition. So if delta is greater or equals 1 minus c, we have a stable multiplex network with the star with the same center. And these two results specify that we can never obtain two-layer multiplex networks with the star with different centers according to definition 4, if we have decay in benefits. And as we can say that for the same condition, the same result, so never a stable network, if we have L layers, but the star has a center with L-1 layer and different center in one layer. And if we compare these two cases with decay and without decay, with all these structure that we examine, for the same result obtained for all layer complete network, we never have, as I said, with the decay parameter, if we have decay, never have these two these star networks stable. But for the case without decay, we have some conditions under which we have the stability. We can guarantee, and this is the difference again with the all-layer star network with the same center with these two cases. So we summarize these results here. And for example, I will show you one short example with 5 players and 3 layers. So the utility function is 1. We have delta is equal to 1, so we have no decay, and C is equal to 1. We show here this structure. So we examine this network G, if it is stable or not. So there are 2 star networks, but with different center in these layers. So we can check these conditions, and we can get that nobody wants to delete or to add links. We check it, and this multiplex network is stable with these parameters. But if C is greater than 1 and delta is not equal to 1, so it is less than 1, this network becomes unstable because player 1 can gain, player 1 can delete this link and will benefit from this. So this network is not stable. But for these parameters, these two networks are stable. So the star with the same center, I mean the star, the graphs are the same in both layers. And here the complete, all layer complete networks are also, it is also stable. What the next step was to examine, to have some general structure of the multiplex network, and we examine networks with the unique structure in all layers. Here we do not specify the structure, we only say that the structure is unique, and this uniqueness of the structure is described in the literature in sociology, because homophily principle said that players tend to create links in different layers, in different ways of communication. So we see here that we obtain here the following result. So if for any layer T and any link IT which exists, the following condition is satisfied, and for any link which doesn't exist in the layer, this condition is satisfied, then the multiplex networks with the unique structure in all layers is stable. And these conditions are shown in this very simple example I will show you. So we have here a cycle network structure in 2 layers with 4 players, and the utility function 2. We have decay parameter equal to 0.5 and C is equal to 1. So all the players here are symmetric in layers. So we need to consider, to choose, for example, any pair of players who are linked and who are not linked, and to check this condition. So for example, we need to check the condition 5 for a link 1, 2 in one layer, and it is obviously satisfied, which you can check it. And for example, for player 2 and 4, we also need to check if they want to create a link or not. It is also not profitable, so this condition is satisfied and this network is stable. So now, if you have any questions for the first part, this is all for our first results on multiplex networks and stability conditions. And If there are no questions, I will switch to the second part. The second part will involve dynamics. Maybe it will be much more interesting to the dynamic theory society, dynamic game theory society. So I will represent you here the opinion dynamics model with two layers. So this is the, how to say, the extension of the model. So the first model, it was proposed by Holly and Liggett in 1975. And it was proposed for the one-layer network when players have a binary opinion, or it will be red or, or blue, and individuals are connected with a complete graph. So this model is called basic voter model. Here, two players are randomly chosen from the network, and they exchange their opinions. So there is a given some parameters of changing their opinion, and the authors describe this stochastic process and find some parameters, for example, finding a consensus, if the consensus is reached, and so on. So this model was extended, and it is called concealed voter model. And it is represented with two layers, an external and internal. In the external layer, we have the same BVM model. And it is assumed in this model that each node has his own internal opinion. So we see the internal opinion layer. Well, it is again the binary opinion. All the players have binary opinion, red or blue. But in this model, the players do not communicate in the internal layer. So we assume that players never tell their internal opinion to the neighbors. And you see each node may have different opinions in external and the internal layer. And in this paper, in this model represented by Gassner and others in 2018, they called these nodes with different opinions in layers like hypocrisy. And they were focusing on the number of hypocrisies in the society and again, if the consensus is reached and the time of reaching consensus. We extend this model and we represented the communication between the nodes in the internal layer. Here, it is only represented by complete network, but I will show that we examine different network structures in layers. So we allow to change the network structure in external and both internal layer. So the motivation was the following, that the network and the players in the society can exchange their internal opinion, so with their close friends. So here, players can communicate and give the real opinion to their friends. And for this model, we have the following notations, very brief. So we have N, capital N, it is the number of individuals, and network G, it is a given network which is not changing over time. And capital R and B represent the external opinion, red and blue, of an individual, small r and b, internal opinion of individual, and the state set for each individual opinion, we have these combinations of external and internal opinions, 4 states. Ri and Re, it is the number of individuals with internal red and external red opinions. And if we write R, it means that it represents the number of individuals with both internal and external opinion, which are red. And we need to set the copying rate, internalization rate, and externalization rate. This is the rates, how we copy the opinion from the neighbors. We explain the opinion from internal layer to external and other. So as I said, hypocrisy, it is a node with different opinions in the layers. And with externalization, the hypocrisy will express opinion publicly. And with internalization, the hypocrisy accepts his previous expressed opinion. So we are interested in the number of hypocrisies as well, and focus, for example, on the red opinion. So this is the focus of our research. So this is the fraction of red external, red internal, and both red opinions. This is the definition. So how to say, we measure the strength of the red opinion by this number. It depends on the fraction of red external, red internal opinion, and both internalization and externalization rate. So we can calculate the number of the whole players depending on the number of nodes in different states here. And I will show you what we are focusing on. We are focusing on two main KPIs. So we analyze this general, as we said, call it general concealed voter model, and we examine and focus on two characteristics. The first one, it is consensus time. The time is called consensus time. That is the time required for all individuals to form the same opinion in the internal and external layer. So this equity should satisfy for this time t cons. And we also focus on winning rate, for example, for the red opinion. So rho is the winning rate of red opinion in series of simulations. So we made a series of simulations and divide the number of winning red opinion by the number of all simulations we made. And the state of this model, this stochastic process, will be given by three numbers. So the fraction of the red external, red internal, and red in both states. And we assume that each stage changing cannot include both internal and external layers. So it will be one layer at each time where you can change the opinion. And for opinion dynamic models, we need to define the fusion rules. And the first one, it is that each individual can randomly choose one of his neighbors to adopt his opinion with probability C. So this same, we set it the same for both layers. C, it is rate. And the second rule, each hypocrisy can become non-hypocrisy through externalization or internalization. So they can change the opinion. And this change is stochastic, so with the given parameters. And we are interested in our research how network structure and strengths of red opinion affect the KPIs. Now I will show one network structure with two layers. So for example, complete internal and external layers, we have this graph. We can calculate, define the probabilities of transition from this state to all possible states, new states. We express here how we can reach the state. So we define the stochastic process. There are given probabilities, and we form the transition rate matrix for this network structure and under given assumptions. We simulate the results, the numerical experiments on different network structures. So the first part, it is the external complete network, but with different internal structures. So this is the star network. We have also we model two star network connecting through one node. It is odd number of nodes. And there are two star networks when two centers are connected with a link. The next group of structures, it is external complete and internal complete. Here also external network is complete, but internal network, it is clique network with the odd number of nodes and even number of nodes. Next group, it is external structure is a circle here, and internal structure, it is a star, the same. So classical star, two stars, and again, two stars with odd and even number of nodes. The same here, we have internal, safe, this circle external structure, and internal will be complete and two clique networks. I will not focus on these experiments. We simulate Monte Carlo. We use Monte Carlo method to simulate experiments. And we did it, the series of experiments for two sets of parameters. They're a bit different. And we focus on the structures. So we compare the structures and how these types of network structures influence their two KPIs. So the winning rate of red opinion and to consensus time. And I will show the results and briefly explain them. So first, the results about external complete network. If we compare the basic voter model with one layer, when we have only one layer, concealed voter model, when players on the internal layer, in the internal layer cannot communicate, and our generalized model, we see that consensus time is the same order of magnitude with the complete network structure, external. So we see for the parameter, the set parameter 1 and 2, we have more or less the same results. So we cannot say that they are different. If we have the most interesting results are about external cycle. So if in the external layer, the cycle structure is assumed, it seems to be a simpler structure, but in comparison with complete, but it was expected that it greatly prolongs the consensus time. So this is the first observation, and but it was expected. And we also can observe, if we compare these two figures, we set all the network structures here and represent this consensus time and compare it. In the left, on the left, in the left figure, we do not have cycle complete network. So when we have external cycle and the internal complete network, because the consensus was not reached in this case for this set of parameters, but it was reached here. But what we can say, the time is much longer, higher. The time is much higher for this type of network structure than for all other networks. And here, it is the average consensus time represented here. As I said, we do not reach consensus here for one type of networks. And you can see that for example, for the first set of parameters, cycle for the external and two-click network in the internal layer has much higher consensus time than other models. Here we have on the another set of parameters, we have the same about a cycle complete. So here we can compare the results. It is interesting. But we can say that not all internal structures prolong the consensus time in comparison with BVM model. Now we focus on the winning rate. So if we consider the winning rate, of course, when we have one layer, the winning rate is highest. So BVM model has, how to say, higher. So if you want to redistribute the opinion for you as an influencer, it is better that players do not have internal layer and they do not communicate in internal layer. So this is the first result about winning rate. The second result, if we consider case cycle complete, as we said, the consensus is not reached. So we do not have. In the cycle complete with the same parameters, it is reached, but it is extremely high. And if we compare here, for example, the winning rate in the cycle and two-click model in both, here for the first set and the second set, it is much lower than for all other network structures. So these structures should be, let's say, you need to focus on them if you want to redistribute opinions. And also here we do not have cycle complete, but here in the set parameter, the set 2 parameters, we have the structure, but the winning rate is very low. Now I'm finishing. So we have, this presentation is based on 2 publications. The first is our working paper. The second one is published recently. So now I'm ready to answer your questions. Thank you.